coming. This presentation is going to be about zirconia and 3D printing and the materials and the production of it. I personally have no stake in the game, so I'm not. This whole presentation is going to be pretty high level, but I hope you'll be able to take at least some key points from this topic and apply it to when you're sort of thinking about next steps for your labs, whether it's materials or technology or whatever. And I'm not in the game of picking and choosing. That is for you all to decide what's best for your lab. My name is Sam Wainwright. I've been in the industry for about 15 years. This is my 10th LMT. This is actually the first time I went, this photo here, looking like a young buck. But I've been at Brontis 3M, CAP, Forum Labs, and now I'm at D&D Dental, where I'm the head of R&D. I'm going to tell a little bit about D&D and our R&D department, talk about zirconia, 3D printing. D&D, R&D, and the team I lead, we really are solving complex problems in dental technology. So if there's a new product we want to evaluate or test, or make sure it works, or compare against others, or even see which zirconia is best, we'll do all that work and present those findings to distribute among the other teams to bring to market. My gift is not working. I've got a fancy gift here. So we do a lot of 3D scanning and analysis. We do a lot of A/B blind studies, a lot of CAD, a lot of printing, and a lot of milling. We have a small laboratory in Midtown Manhattan with about 6 people. But we are purely an R&D facility, which is really an unbelievable opportunity for me. So let's first talk about zirconia. So demystifying zirconia a little bit. You all have known zirconia. It's been around for a long time. It's back in mid-2000s with 3M, and even Procera with aluminum. But zirconia has really evolved a lot over the past 10 years, as you all know. I mean, it's really competing with Emax correctly now with the next generation, which is a lithium disilicate, and others. And it's now the most used material in the dental industry. There's 2 key parts to zirconia. There's the yttria content, and then there's the flexural strength. And they are related to each other. So there'll be classifications of yttria, and it's by mold percentage. But so there's a 3, 4, and a 5 line. That's really the yttria class of the zirconia. And there is a correlation between strength. The lower yttria, so the 3Y, is the strongest zirconia, and the 5Y is the most translucent, but the least amount of strength. So that that give and take is really should help you all understand, like, when you're looking at materials and when you're setting up a portfolio or trying to simplify or condense down your offerings to your customers, think about what classes of zirconia that you want, 3, 4, 5Y, and what strength advantages or disadvantages they have accordingly. And of course, that image should have been gone. There's monochromatic and multichromatic. There's benefits to both. Monochromatic is just dead, one shade throughout the whole thing. I shouldn't say dead because it's a really bad term, especially with bad sintering. And then there's multichromatic, so it's got transitional color. I will say multichromatic is really is the more aesthetic choice, obviously. Transitional color looks more lifelike and has vitality. But you also have to consider that these transitional lines are going horizontally or parallel to the puck's height, right? So nesting then becomes really an important criteria. And you can't just throw units in. You have to make sure that your bridge, or even single units, you have incisal or cusp tips going through the incisal range of the material. And each material, each multichromatic zirconia on the market, could be different in the way it's distributing those colors and those translucency ranges. And then pretty recently, we've been seeing a lot of multi-yttria. So there's multichromatic or multi-layered single yttria materials in the market that could be a 3Y, 4Y, or 5Y, but now there's transitional color and transitional yttria. So it goes from incisal from a 4 or 5Y down to a cervical of a 3Y. So you get the translucency on the incisals and your strength around the margin of the restoration and your opacity, maybe blocking out a dark stone. There's a lot of promise in these next generation materials. But there's good and bad with everything. There's no perfect solution here, of course. The good is multi-yttria could be an all-purpose solution for labs. You simplify down your products and maybe have just one product that does a lot of what you're getting prescribed. And like I said, it has the strength where you need it and translucency where you need, right? But the bad is it's fairly new to the market, and we're all a little bit gun shy on new things to market. You sort of want to see where it's landing, what becomes like the best in the market. And a lot of them are very, very expensive. So like when you're thinking about your zirconia portfolio, right, cost has a big impact here, right? You don't want to have your economy crown milled in a $200 disc because you're going to be losing all that money on boosting material costs. And then there's complexities of mill setup. And I mentioned this is multi-chromatic, which that's important. You know, you want to make sure the transitional color looks natural, but it's even more important with multi-yttria because you don't want the tail end of a bridge leaving that 3Y zone when you think you're getting full 1200 megapascal strength. You know, so the way the part is positioned becomes even more critical. So like these are just like process considerations, and like you really have to have good standard operating procedures around these things, especially with these multi-yttria, multi-chromatic materials. And then there's perception. If anybody knows clinicians report, it's a bit of a joke because it's Gordon Christensen. There's actually a couple reports, kind of co-sponsored or not with Glidewell, around abrasion of 5, 4, and 3Y zirconias. And although the science, and I look through the numbers, is a little they're publishing to the market that 5Ys and the higher Y zirconias are more abrasive to opposing dentition than 3Ys, which is a little bit ironic because when zirconia came out, you all remember opposing dentition wear. What a terrible thing. Now they're saying 3Y is the choice for opposing dentition wear, which originally the whole thing against that was 3Y zirconia. Now they're talking about it in this next class of materials. So you might have some customers and dentists that have this perception, and you need to be able to speak to that. And Gordon Christensen in Clinician's Report gets a lot of eyeballs. So that you should just be aware of that going in. And then you're all familiar with the ident ceram, that really has the specific sort of makeup of the zirconia material you're using. And so how it's made, there's really 3 main ways to make a zirconia disc. There's slip cast or chemical bonding. It's pretty much a slurry, and then it evaporates out and solidifies into a disc. There's a uniaxial pressing, which is the top one, where the powder's put in with this mixture of pigments and all that, and it's pressed from top and bottom. And then isostatically pressed, which is put into actually a water chamber, and a pressure is applied to the puck from 360 degrees. Now, I have the most experience with, and I hear the most sort of consistency in manufacturing around isostatically pressed, but I'm sure there are some very good chemically bonded or uniaxial pressed materials out there. I just don't really have a lot of experience with them. For example, Glidewell's Bruxer is chemically bonded or slip cast. So it's a very well-known, very sort of brand name material that uses chemical processes. So this is one input, and what's really tough about this is you can't really make any broad conclusions from the way it's manufactured because it really is about the manufacturing process itself. And unless you can go to each of these zirconia materials factory, you really don't know how tight those controls are, how good those sort of amounts of yttria or the pigment are added, and how consistent that process is, especially from batch to batch. These discs are made in large batches from 100 discs at a time to thousands. And batch to batch means that, like, is the batch from October the same as the one made in January? Are they the same shade? Because the last thing you all want as a lab is all of a sudden your shades to be different and due to nothing that you've done differently. That batch to batch manufacturing is really hard to tease out. And I think that really comes through good control of process and understanding what expectations are in your materials. So some considerations, right? So you've got to put Arnold Schwarzenegger here, competitor, but are you getting a lot of requests for brand specific materials? And are you providing it? So do you have a big Bruxer business and do you mill Bruxer? Is that a part of your portfolio? Really, the whole point of this slide is you want to offer as few materials as possible because it's just less process sort of change, if that makes sense. You want to have a concise, consistent portfolio that you can talk to and sell to your customers. And what does that mean? Is there a high strength 3Y material in that portfolio? Is there a high aesthetic single sort of 5 or 4Y of a 900 megapixels? And then do you have a premium aesthetic? Do you have that $250 disc as that multi-yttria sort of cutting edge material? But the whole point here is like a single manufacturer likely makes sense, and have a simplified portfolio. You don't want to be stocking in inventory. And I'm preaching to the choir here, I'm sure, but simplify down your portfolio as much as you can, because with pre-shaded materials, because white zirconias are pretty much out the door at this point, maybe other than screw tape full arch bridges. It's a lot of material to be holding on the shelf. And you never want to be in a situation where you're trying to run lean on material, and then something's on back order, and then your A2 is in the mail, and the case is delayed, right? That is not a very good feeling. But what's right for you in your lab? I mean, this is really where the rubber meets the road. How much do you want to evaluate zirconias, right? How much testing? How do you choose material is really testing, milling, and comparing, right? A pretty simple process of, I'm considering these two brands of materials of these classes, but this is the class that I need to solve in my lab, or it's a hole in my lab, right? Mill the same two crowns and evaluate them. Have all your techs look at them and evaluate them, right? But that takes time and money. Support and process matters, and what I mean by this is how much effort you all want to put into this will depend on sort of what sort of makes sense as a partner or a provider, right? Somebody who does really great documentation that are maybe based in the States, you can get them on the phone, you work with them on other products, that might be a lot more turnkey for you. And it might just be a much more trusted workflow that you'll have access to a support team. And the reason I say this is because there's a lot of zirconia materials in the world, but that beautiful one in whatever country it's coming from, they might not have that same support network. So do you have those internal resources to do all that validation? And also just making sure what you're getting is consistent with your product. So I think there's a lot of value there, and the partner you choose and how it's being supported, the documentation is really an indication of how good that relationship's going to be. And so if you have those lab resources, if you have an R&D guy like me, you can really use any material in the world, and you maybe can unlock better pricing or direct sort of engagements, because you have this sort of that back end, you know what you're getting yourself into, and it's not causing you more headaches down the road. This is a common mistake in our industry, is a lot of people will go to tend towards the lower cost option, but in the actual use of the product, it's actually costing many more headaches and time, and it's actually costing you more money. And then the worst is if those products start flowing out to your customers, and then you start getting those calls. That is never a good time. So what's the best, what can you spend the time on? What do you all want to, what does your portfolio ideally look like? And how do you want to use your internal resources wisely, right? And the next couple slides I'm going to talk about, manufacturing zirconia is key to consistent product. And there's some best practices here. And the reason I say that is not just like in normal production, but if you're evaluating zirconia, if you're not sintering it correctly or whatever, it's not a great evaluation, right? So these are some tips that I have on how to, just high level, simply put, make sure you are doing the right things and focusing on the right things to have consistent throughput. Sintering is everything for zirconia. There are, especially with some brands out there could be 4 different sintering cycles, 5 different sintering cycles for one material. And then you look at their portfolio, if they've got 5 materials, there's like 15 or 25 different sintering cycles. Think about like somebody loading a furnace, right? And picking and choosing and batching units in a sintering furnace. The simplification of your portfolio will then lead to the simplification of your workflow, is my point, right? And you never want to overload. Always sort of talk to your sintering furnace manufacturer and what they recommend in a full load. And I would say take 20% off of that. Overloading a furnace is never worth the extra couple units. Always use the right sintering cycles. And what I mean by that is there could be a speed cycle, a standard cycle, a bridge cycle, and then a long bridge cycle, for example. Don't put your bridges in with the speed cycles or the standard cycle. Sort and batch those sintering cycles appropriately, because you will get different results or worse results or something that is unexpected. And really keep your unit count down and try to keep your process as consistent as possible. So if you're stacking multiple trays, say you're doing 2 trays with lids, even if you're only doing 5 units, put the 2 trays in. That energy load, that mass, is really critical in having consistent firing and temperature ramps. And extra furnace capacity and redundancy is a good thing, and I mean that on the furnace level. You don't want to be running everything at max, always. You're just going to start to have misfires. So what I mean by this is invest the extra money and have a full furnace as capacity. So then you can do these smaller batches where, oh, I've got a couple bridges I need to fire. I'm going to do those on their own in the right cycle. That's huge, but if you don't have that extra furnace, the rest of your production is going to get slowed down, and then maybe you start missing timelines, right? So it's painful, but redundancy and having capacity is critical. Less zirconia, fewer cycles to manage, and have those cycles clearly printed out at station, entered into the furnace, dead clear. So anybody that's loading and batching your furnaces knows exactly what to use. And even do like a group training on it. So everybody, even if they're not running the furnace, everybody knows what's going on and what to do with what material and what process. And you will get much, much more consistency. Sintering is everything. And this is a huge one. Thermocouple and heating elements in furnaces have a life. Do you all know what your number of hours for your thermocouples or heating elements are in your furnaces? No, he's my engineer. Every manufacturer has a certain amount of hours that elements will last. 1,000 hours, 2,000 hours, or whatever. And the furnace itself will have a total runtime, right? You want to be proactive with heating elements and thermocouples. Because if those are bad, or they start going bad, you're going to be hunting down shade and opacity issues. And if you're not tracking what units are coming off of what furnace, like if that isn't clearly managed and tracked in the process, you're going to be question mark on what is going on, right? So be proactive and not reactive with thermocouples and heating elements. For those that don't know, thermocouples are pretty much a fancy thermometer in your furnace. The heating elements, they're going to be 2, they're going to be 3, sometimes 4 or 5. They're the elements that heat, right? Degas and purge on schedule, as the manufacturer of the furnace recommends. Some furnaces don't call for degassing or purging, but fundamentally what this does is it cleans out contaminants in the model. And on MOSI 2 type heating elements, it actually can heal them. I don't really know what that means. I've never seen anything heal, but do those cycles. Stick to the manufacturer's recommendations. It could be once a week, once a month, but have that consistent maintenance cycle and proactive sort of adjustments as needed. This is the big one, calibration. For years in my previous life at CAP, we used Phoenix rings, and I realized after really digging into it at Dandy, we were using them wrong. Ferro PTCR HTH rings are the only ones to use. I talked to many, many experts in the industry. Every other one, just throw them in the bin. These are the ones to use. They're like a Garland dental supply or something, $70 for a pack of 15 or something. They have a very, very specific long sintering cycle they have to be run on. You can't just throw these rings into your normal sintering cycle. You will get a false negative or a positive. They also have, by batch, if you notice this number right up there, 451, each ferro ring can come from a different manufacturing batch, and they all have their different conversion table associated with it. So what I mean is, you go buy 2 of these boxes, and they could be from different batches. They have a different table you have to refer to. So when you read out your measurement, that could mean you're at 15C, 1500C, or 1550 or whatever. So make sure you're using the right conversion table with your batch, and make sure your measurement tool is really calibrated and accurate. This is a really slick one that actually Ferro recommends on their website, where it has this nice holder. How it's meant, you don't want to be doing this by hand. It's expensive, but it's well worth it. The proper alignment, be able to take measurements from a couple different rotations, and averaging those numbers out, using the right sintering cycle for the ring will give a super accurate temperature reading. So when it thinks it's going to 1500, it will tell you actually what it's going to. We had a furnace, I won't say the name. It was at 1600 C when it was supposed to be 1500. We ran it again, 1580, way off. Like 80 C, 100 C, way off. We opened up the lid of the furnace. The connection to the coils was melting. The furnace was running fine, no errors on screen. It was a fire hazard. This thing would have caught on fire if we didn't know to look. So just an example, like these furnaces are super dumb. And the fact that like thermocouples are supposed to know the temperature, okay, well why didn't the thermocouple adjust or say something? Because 100 C off is significant. And your zirconia will become brittle if too hot, or very opaque or dead. That's the bad word in zirconia. It looks dead if under fire. And then expectations will be missed, you'll get remakes, and doctors will call very unhappy.
Where do you get that?
I found them at Garland Dental.
Oh, Garland.
I've never really worked with them before, but they're the ones that had the ferro rings in stock. But these are the ones. So this PTCR HTH, they have a bunch of different class rings. Those are the ones for our temperature range. And follow their instructions from Ferro's direct website for cycles.
Should you use that specific caliper too?
I would recommend it.
Okay.
This thing with the fixture, it's not cheap, it's 800 bucks. But worth the money. And this process, although it's a full 12-hour cycle, it stinks taking a furnace out for that long. If you did this across your furnaces once a month and log those temperature hits, you can actually draw a curve, and over time, you can see your fleet health. You can start, oh, this one was doing really good, and all of a sudden it's dipping down. You know, let's check the elements, let's do something. This is all about being proactive and sintering. Zirconia, like everything else, is secondary to sintering. If you got bad sintering, it's just setting up for a bad time. This is a way to really control a fleet of sintering furnaces, and especially if you have lots of different types of furnaces. 1500 C is 1500 C. I don't care what kind of furnace it is, and don't overload your furnaces. And root cause, so finding where defects are actually happening. This is easy to say, hard in practice, but there are many, many steps to the life of a crown being made, right? And if you have hard stops and checks throughout, you'll be better able to actually point to an issue. And what I mean by that is, like, if you have a chip margin, right? Did that happen from the mill? Did it happen in singulation? Did it get dropped? Sandblasting, adjusting, finishing. You just know the QC station got a chip margin. You could be replacing tools, you don't even need to. You could be calibrating mills, wasting time. So, like, the simplest one to do, and I'd recommend everybody do this, you're probably all doing this anyway, I hope. Right when the mill's done, look at the disc. Check the margins under a microscope. At least 10 or 20 pounds, loops or something. Check for chip margins right then and there. And if there are chips, log it. If there are not, log it. So then if down the road, a unit off of that batch, and there's a lot of, like, you have to really have a unit sort of like audit trail a little bit here, so it's tough to build. Everything I'm saying is like easy in theory, right? But if you get a chip on that unit that you passed out of the mill, at least you can say it's not your milling machine. Like, how nice is that? And move to a culture of, like, learning and improvement, not you're in trouble for messing this up. If somebody messes up a margin in singulation or drops a crown in state when they're loading into the furnace, get into the mode of, like, look, we're human. Let's learn, let's improve. Because otherwise you're not gonna have people chiming up and saying, hey, I messed this up. And think about this, if a unit gets messed up in singulation, and you catch that then and there, and you remill it, versus it going all the way through staining lathes and not to QC getting caught, how much time and labor are you saving right there? It's huge. Solve the right problems with data and process controls and checks. Remakes to human error are hard, right? That is a training, it's a people thing, but remakes due to process. So, like, you might tease out, we're moving this set of discs or this tray for whatever. it's too far and it keeps getting dropped, right? You can change that process. You can move that station or whatever. So the more you understand your process and where the problems are actually coming from, the better your process will then become as a result. So the conclusion is equipment and process is fundamental to the production and proper evaluation of zirconias. This goes for the materials you're doing today or any materials that you want to move into in the future. What do you currently offer for zirconia crown products? I would make like a little chart, right? Okay, I'm offering these 6 right now. Can I get rid of one of these and make a product group to one, right? The less materials, the better. Simplify where possible. One manufacturer is best if you can. You can have it all under one manufacturer, one place to order it from. Always ideal. And tease out the problem areas through internal or external through root cause and feedback. So actually, I didn't make this point, but like externally, the doctor says remake the crown. Find out why. Get specifics. A remake is pretty broad. Like, what is really the reason? Is this something that your lab made a mistake on? Is it a misfire? Is it shade? Is it fit? And then you can actually start to understand maybe nuances to working with that person, as we all know, right? Or preferences, and then sort of take that into consideration. This is actually a flow chart I set up to log all the steps of milling. It's actually very complex. It's deceivingly complex. So when I went into this, I was like, no, it's going to have a couple of bubbles. It's like, anyway. So 3D printing. Any questions on the zirconia before we move on? Yeah.
Yeah. So how do you test the advertised strength of zirconia?
So without being able to meet the ISO standard, because there's a long PDF on the ISO standard that all these materials should be sort of set at, is actually quite onerous. This is not a great answer, but you almost have to just assume it's fairly correct. You can maybe ask or push the manufacturer for their reports, or it's never a one number. It's always a range, right? Are they averaging it for top, bottom? But it's good. It's very, very difficult to do it yourself because you need to polish, you need to get the machine or outsource it to a firm, which is very, very expensive. And let's be honest, zirconia is way stronger than anything else, right? So unless you want to offer a 5Y 600 megapixel to replace Emax or something like on the lower end, where strength can really maybe make a big difference. Anything over 900 MPa is stronger than anything else. I mean, lithium disilicate pressed is what, like 450? Milled is like 375. It's not even close. So, not a great answer, but yeah.
What's your experience with different thickness configuration of the prosthesis itself? For example, like a 3 unit that has different thickness, different spots, versus a full arch that has or requires a stabilizer sender. I've seen people not even using stabilizers. And I don't even know how they can make it through, but
it's like throwing a dart at a wall. Stabilizers are critical, and the right cycle is critical. So in all, like I said, there's like 4 or 5 cycles per every zirconia, right? Some of them even are so prescriptive as like 4 to 6 unit use this, 6 plus use that. The right cycle and stabilizer on each unit. Actually, I remember back in CAP we did every other and it was better than every unit on stabilizers. Do you remember that thing?
Yeah.
Yeah.
Too many is not good either.
Yeah, too many is not good. That's the difficult and the fun part about dental. There's no easy answers, but stabilizer, absolutely. Bridges, luckily we all have 5-axis mills now, but like if you're using multi-chromatic, multi-layered zirconia on a bridge with a stabilizer, you need to be fully enabling on that 5-axis to get those paths of insertion, right? So like your color needs to be set up optimally, you need to do stabilizer, and I think the big point is, I would make here is like, CAM is actually really, really, really important, and more so today than it ever was. Job setup, that being correct, it's like CAD. If it's bad CAD, it's going to be a bad product. Bad CAM, same thing. It's all about that sort of front end work and not being rushed, proper training, the right sintering cycle, and you'll hit it. Thank you. Yep. Yes.
What about stabilizer size? Is there like a ratio depending on the size of the bridge? Does it make a difference?
Yeah, it depends on the CAM software because they all have their different sort of shapes and sizes.
Yeah.
And usually they'll generate based on the size of the part. And I don't even remember. It's been a long time since I've used the Millbox, but in Hyperden, it goes from a full arch with a hole in it to a half arch.
Trust the software.
Yeah, and I think every other unit would be my best guess for lingual supports. So don't do every unit, but every other. And it's going to be your best shot. Nothing's perfect. Nobody in this room should ever expect a 0% remake rate. It's too nuanced a process. And if you do, please, I want to talk. Yeah.
So we recently switched over to the multi-yttrial zirconia.
Yeah.
And my question, and our manufacturer didn't really give me an answer that I was satisfied with. But if you have a 3-unit bridge where you're hitting some of that incisal, even in the connectors, how is that connector not considered on the smaller end of the megapascal strength? So if it's creeping up into that 600, 700 area,
Yeah.
how is the whole connector not considered that by the weakest point?
I think it is.
Thank you. That's what I thought too.
Yeah. And there are different, in 3 shape, when you do a cut, you get like the square millimeters.
Yeah.
I would ask for, I would switch the question around and ask them, maybe not on that material, but like, say they have a material that is a full 5 wide, it's a 900 or 800. Ask them what you would do for the connector size for that material, right? Is it 12 millimeters squared, 14? And then, the tough thing is when you only know this problem until you bring it into camp and design's done, right? And you don't want huge connectors, and you also don't really want to be sharpening your embrasures because this is glass. You're scoring it. It's weakening the structure. Especially, you should always be doing that green state as much as you can because it re-solidifies the part. But it's a tricky one. But I would assume the worst always. And I think you're spot on. I think you're right. Yeah.
I've noticed sometimes that when you were mentioning about connectors, I have noticed that when a bridge breaks, it is sometimes in the connector where we individualize a little bit more on the green stage. Although the connector is still very solid, very robust, does the shape of that individualization has to do?
Yeah. I mean, doing a green state is definitely the way to do it opposed to post-sintering, even with irrigation, right? But you're fundamentally making a score. It is a healed structure. And also remember, in 3 shape, if you're looking and you're at a 12 millimeter squared, you don't really know how much you're cutting out of that total surface size, by hand. So I would bulk up the lingual connector. Like give yourself a bit more strength on the lingual, and also the transition from the lingual surfaces of the teeth. Maybe make it smoother and more cohesive, and I think you'll be able to get away with a bit more.
But the shape of that cut, if you use a wider disc when we are trying to individualize a little bit more, instead of coming with a thinner one at the beginning stage.
Yeah, it's good.
Could make a difference.
Yeah, it's a good point. Because you don't want it to be a sharp tip that you're finishing down to. You want it to transition. You want it to be smooth, right? So so much so you almost want to start with the broad one, and then go in and try to, if you can see, smooth. So it's not a sharp transition from one to the other, but it's actually smoothing out those corners. Corners are bad, period.
Okay.
And I would say the same for margins. Corners are unequivocally bad. They chip more, they're prone to failure, and they're weak spots. But yeah. Okay, anything else? 3D printing. Which time? Oh, I got plenty of time. Wait, no, it ends at 12:30?
No, same here time.
Oh, 11:30?
Plenty of time.
Okay. 3D printing is a good one. All right, expectations of 3D printing. There is no 3D printing system. don't care what anybody tells you, I've used a lot of 3D printers. They all have their good and bad parts. Great. If I could mash them all together and make the perfect product, I would, but it doesn't exist. I've used a lot of systems. I wouldn't say I've used all of them, but I've used a lot. 3D printing is very simple in theory. You can be sold a book of goods that is a process that is magic, but it is not. It is actually very complex in theory, in reality. And the chemistry is extremely complex. The transformation of a liquid photopolymer to a solid is a very complex chemistry. I've worked at Forum Labs for 4 years. I worked with material scientists building these polymers from the ground up. The amount of revisions, the amount of testing, aging, toxicity reporting, long-term, short-term, is extremely complex. I think we had 30 full-time chemical engineers and scientists on staff. And they don't even release that many products. I mean, it's truly a under sort of talked about thing. This is a very complex process, and process matters. Not just the printer itself and what is baked into the process, but also the process that you are all deploying in your laboratories. And every step of the process can make or break the part's accuracy. That goes from how the resin is stored, if it's shook up, how the tank's treated, job setup, critical, how it's supported. And the CAD is critical, especially for models. Having the right wall thickness, solid versus removable dies, articulator backings. Good CAD makes good production, period. And 3D printing is generally sold at, and you'll see here, I have no skin in the game, I don't care anymore, right? It is sold as simple. Look at, we've got all these beautiful machines, just bum, bum, bum. Look into the details. Look at their specific instructions, what they have online. Because it is really, there are some that have a pretty good seamless process, but the devil is definitely in the details here. And like a one button print and production system, like minimum 5-10 years out. Like it is still a very new technology, and I think a lot of people forget that. You know, in dental milling, right, from the lava form with lava and those blanks, right, in 2005-ish, to where we are today, like it's very mature, right? It's plateaued in technology. You're not seeing much else, more disk changers or whatever. And maybe some improvements in the software side, which is good. But milling has been, as humans, we've been doing milling for a very long time. Maybe not totally computer-controlled milling, but it's a very known quantity. 3D printing was invented in the 1980s. And the fact that we're 30, 40 years in now, oh no, 40, you know, I think that's, you should keep in mind. Like, photopolymer science and chemistry is very new. 3D printing is very new, and there's a lot of ways to do it. And the ecosystem really matters. And a lot of people will sort of skim over it. They'll stick to the sort of like the big talking points. But there's really 3 buckets that you think about, right? There's the nesting software. The software, I've seen good and bad nesting software. And what I mean by that is ease of use, repeatability. Can I train my mom to do it? I call it my Linda factor. There's so many out there that like, I could not train Linda how to do this, right? That's really important. And like, you have to think about delegating work out in your lab. You want as many people to be able to do these processes as possible so somebody can call in sick or you can pull a butt, right? Then the actual printing itself, and then the post-processing hardware, build plate, the hardware like the resin tank, the build plate, those sort of elements that you're interacting with all day. And then post-processing, wash, cure, and finishing. And what I mean by finishing is like, what's the guidance? How do you finish it? Any special handling? Anything like that. Application guides and support, documentation online, the website, how easy these things are to find, to put into your own SOPs and just implement on, will give you a really good indication on how well the product is figured out. The maturity of the documentation is a really good sign. And consider all things. Don't just focus on print speed or the one resin. It is really, it's hard to do, but you have to take a step back and look at every step of the process and make sure it all makes sense. And there's an answer for it too. A lot of times put a system in like this and there is no answer, and then you get into the danger zone where you're making it up as you go, and that's dangerous in 3D printing. 1080p is dead. Nobody buy a 1080p printer today, please. 2K or up only. Build plate size makes a huge difference. It makes everything easier. These tiny build plates, unless you want to run a whole farm of them, which I ran a 20 printer farm, it's not fun. Get home, my kids can't even touch me because I've got isopropyl and photopolymers all over me. Skip 1080p. We're finally to the point where like there's great viable printers with good build plate size. So that's the technology of yesteryear. Nesting software, the speed of use and the process, and especially if you're doing multiple applications, right? Say dentures, splints, models. How is it with each? Because they kind of all have their different ways they like to be set up. Otherwise, they're not accurate, or you have Z-bleed, or you have delaminations, right? So, and if you're not bought in yet, go and look at their documentation, talk to their support teams, get their videos online, and understand it fully before investing. And if you have a system and you're just struggling with it, do the same and push to find answers if something's not working, especially in a workflow in nesting. Tank and screen life. A lot of people don't talk about this, but if it's an LCD-based printer, so the way LCD printers work is there's a ton of light from an LED being projected from the bottom, and there's an LCD mask that turns on and off pixels to let light in. An astonishingly low percentage of light, but that's the way LCD printers work. There's a ton of heat, and those LCD screens wear out. They have a certain amount of hours to them. They're getting better, and I think this is probably going to be the technology of the future because it's so cheap per pixel in hardware versus DLP. But they need to be replaced. So it's not just about the life and how many parts you can get out of that life, but it's also how easy is it to replace? How expensive is it? Can you replace it without messing it up? It's like user replaceable things, but can the user actually? Can Linda replace it? Right? If my mom can replace it, we're in good shape. And tank. Tanks are a burden. If anybody tells you otherwise. Although Formlabs probably is my favorite tank. They're worse in many other ways, but the tank in Formlabs I wish was on the tank on all printers, to be honest. But there's pouring, cleaning, storing, filtering. There's age of tank. It affects everything. Is 3D printing is the light getting to the resin, and anything in between, either glass or the tank film, is in between, right? So that the life of tank makes good prints. The way it's handled, the way the surface, the part peels as it lifts, it all makes a huge difference. And if you clean it incorrectly, you'll start having bad prints and delamination. So delamination happens when it can happen right off the bat, but in the middle of the print, all of a sudden there's a shelf and it kind of sticks to something that's hanging. Looks terrible. That's a delam. That's you have one layer to another not adhering to each other and they split. You ever get a pancake in your resin tank? Right, that's a delam. That is not enough energy to bond to the previous slice. That has a lot to do with nesting and tank. Also the optics, but don't get me started about optics. Okay, post-processing is never really talked about, but it is so critical. Isopropyl alcohol percentage purity. How often should it be replaced? Is it small batch with constant cycles or big batch with a large amount of isopropyl with then floats to measure the percentage and stuff like that? That process has a lot to be desired, to be honest. And isopropyl is not fun to deal with. And just understand completely what you're getting yourself into. And if you're struggling or you're having sticky parts come out, when you're fitting the crown to the model, and you're like, why is this sticky? That's a sign you've got bad washing. And probably my biggest pro tip here is when it's out of the wash and it's still wet, hit it with compressed air. Makes a huge difference. And rinse again, do it again. You have no idea how many times I've done that in my life. Headphones in though, it's very loud. And scalability. More printer types and resins, the more problems you're gonna have. That's probably the most difficult thing here is like, you wanna buy I have a whole section about what to buy or how to think about what to buy, but you don't want 3 different printer types and 3 different post-processing UV post-cure boxes. It's just going to make your life chaos. So try to stick to one or very few if possible. It's a very hard thing to do, especially if you're just getting into the technology. And buy for the application. So what do you want to print? The first thing I ask anybody that asks me about 3D printing, what do you want to print? If you just want to do models, it's a much different conversation than models and dentures, splints. So what is really your print? And if it is dentures, is it a want to convert your customers to printed dentures, or is it a need? That can sort of adjust how sort of you're thinking about your appetite for this endeavor, right? Documentation, process, and support is critical, especially for biocompatible. I have a whole part on conformance, but it is really a tolerance for risk, and also how much time you want to put into process development, because these 3D printing companies will not show you how to set it up in your lab, really. They'll give you the big steps, the tools, but those in-betweens and what is actually being done step by step, most of the time isn't really told. So you have to sort of set that up and train your team and get Linda producing, right? My mom's the best, sorry. I shouldn't stop saying her name, she gets mad when people say it. She's seen one of my webinars, she's like, why do you say my name? It's just a good, metaphor. And simplicity works best. Like, you want a complete and concise process, but like try to reduce down. Like, you don't want to come into this thinking, I'm going to do surgical guides, splints, hard, soft, I'm going to do denture teeth with milled teeth, and it's like, okay, slow the roll. I mean, you can build into it. It's certainly viable, but it's a lot to take in. We're not even talking about the CAD side. CAD is its own ball of wax at making that work. But and a bonus material here is if you're thinking about getting into 3D printing and you're not, and you want removable dies, it's not possible. Okay, solid check models, extra dies. Just putting that out there. Everybody always has these expectations of removable dies. It is not consistent. Nothing that I'm happy with. Depends on your level. Just what you accept. I don't want to adjust dies. So solid models, please. Anybody doing removable dies? Do they work?
Yeah, removable. No, it's great. We have the solid and the extra dice.
That's it. Ding, ding, ding. That's what it's doing. Open and closed. So I'll preface this section a little bit. We all remember the open and closed mill wars of 10 years ago, when you had different disc sizes, D-shaped ones, and it was open and closed, and they were fighting. This is much different than that, because zirconia systems are much less risky in process and regulatory. Even if a zirconia crown is sintered 100C under, which is like worst case, or over, it's probably going to be okay, right? That is not true for 3D printing. 3D printing, if you send out an uncured part, it is a long-term risk, guarantee it. These things can be dangerous, toxic. The advantage with that said, the advantage with open systems is you can do what you please. You can put more material in it, you probably get the printer for less and get material for less. So there's savings to be had there, right? But just keep in mind that there's not going to be that support or that process for you to build on top of. So this is kind of like what I was saying about zirconia. If you've got the resources or the engineering talent or the team to be able to take an open system and make it work, because a lot of times with open systems and open materials, if you read the instructions for use, it has general guidance, whereas a more specific closed system are very specific. And those general IFUs leave a bit to be interpreted, and there's risk around that. So is that something you want to go down? And I will say Asiga's here, but I think Asiga, out of all of them for an open system, is quite good. The ones I'm mostly talking about here are these $500, igloos or whatever. Do not do biocompatible on those systems unless you really, really got your ducks in a row. And you are doing the process completely correct. Otherwise, it's just risk. I mean, who wants risk? Doctors don't want to, get a call when they're on the golf course, and then they'll yell at you about it. Closed, less risk, so you can have biocompatible products that have more guidelines that you can plug in and make your own, and has documented process, and it's formulaic in development and scaling. So what I mean by that is like, opposed to having every resin on the market with general settings, they'll probably have a much smaller portfolio, and really tune and validate to the nth degree these resins and workflows. And at the end of the day, what's most important, the resulting compliance. But there are sort of two closed system types I will call out. There's closed, which is only their resins and their materials. And then there are like carbon, which has some of their own resins, but then there are also, they have their own third party, like then supply Lucitones on their system. They have this third party network and connection. So you get a bit of a bigger portfolio. So just some things to consider about open and closed, that it's much different than million zirconia. I know everybody's a little bit gun shy about how that all went down to 98mm discs, but it's a much, much different thing. And conformance, I've already mentioned this, but IFU is the truth. IFU means instructions for use. Everybody, if you're making, say, 3D printed dentures and splints, have the materials IFUs downloaded and on a company network drive, and make sure everybody has access to them and you can print them out and read them. If this is the constant thing I hear all the time, I did this work for years in an analog product. So say Lucitone, traditional acrylics. Oh, I did this. It doesn't fly in 3D printing. You can't just do that. We cannot make it work with 3D printing. You have to be very, very formulaic. There's SDS, which is safety data sheets and IFUs. Have them available. Make sure the team is aware of them and read them. They're boring, but read them. They're not that long. No heat. No, outside the IFU. So if the IFU doesn't say, and you're introducing heat or additional solvent or additional UV exposure to the process, that is a deviation from instructions, thus making a non-biocompatible product. And a big thing here is like, you know, these post these GC OptiGlaze and stuff, and you need to post cure them, right, for characterization. You're hitting that with additional UV energy. The more UV energy you put into a photopolymer or a thermoset, the more brittle it becomes. It's going to explode. So you can do those things, but my big point here is if you're going off of IFU, or if you're unsure about some specific process that's coming up in your lab, confirm it with the manufacturer or your provider of the printer. And you can get like an okay. And if you get an okay and it's off IFU, document it for your records. In an email is, I think, formal enough. I'm not a lawyer, but have it somewhere. It's about risk mitigation. And do not mix and match. Do not wash Lucitone denture base with Keystone soft splints. They need to be in their own solvents, period. This is actually pretty nice. You know, there's no perfect wash solution, but these are in an orbital shaker, which is nice because then you can have buckets dedicated to the various products. So you don't have to have 5 different washing units. But even this, I mean, so like the IFU could call out using an ultrasonic. We had to email and write to the company and be like, can we use an orbital wash? And what would be the equivalent 2-minute cycle in an ultrasonic? And they came back and said, yes, that's okay. This is how long you should be doing it, but no more. So if you're changing even this, make sure you get it officially written. Otherwise, you could be making unsafe products. And it's not worth the risk. I don't care how, you know, you might save money on the front end, but on the back end, it's not good. And I guarantee in the lab industry, if we get more regulation coming into our industry, the first 2 things they're going to look at abutments, implants. I mean, they already done this. There was already all that. Was it 5 years ago now with the whole thing? Only hand milled abutments. Anybody remember that? Yeah. They're going to look at implants because it's class 3 and 3D printing, photopolymers, guaranteed. And have a clear process for your team. Get cross-trained. Get everybody on the same page. An environment of learning and growing. And you can make mistakes. The only reason I know about anything about 3D printing is because I've made every mistake. I printed a model on top of a model. Okay? And it printed, and it was awesome. It was so dumb. It killed the tank, but it's So the conclusion is, buy for what you're doing. Keep it simple. Start out small. Ecosystem and process really, really matters. Do you want a turnkey, single source provider for everything? Or do you want to build it yourself? Both are very viable, just how much time and effort, and what do you want to do here? And then clearly define your lab's process, do's and don'ts, guardrails. No one else will. Nobody else is going to come in and say, you should really be doing this, or, so you are the owners of your futures. I hope this has been helpful. Any questions or anything like that? Closing this out. No?
Thank you.
Okay.
Yeah, very good.